Good afternoon, ladies and gentlemen. I think we'll get started a few minutes early and do this introduction prior to the Berkeley time of 10 after, because we do have a very full agenda today and two very distinguished speakers who are going to split the time. So first of all, welcome. My name is Gary Baldwin. I'm the Director of Special Projects for Energy and the Environment at CITRIS. And I would like to thank, first of all, Infineon Technologies for sponsoring the lunch for these weekly events. Hello to our web viewers, and I'm told by Kosroff that we have more than 30 websites logged in, but especially to our sister CITRIS campuses at UC Merced, Davis, and Santa Cruz. In the back of the room, now that all the lunches are gone, you may find flyers for our I for Energy seminar series, which takes place on Fridays, sometimes located in this room, sometimes located in room 250 downstairs in this building. And also mention that on October the 20th, we have a distinguished speaker, the former CTO and CEO of Samsung, at 4 p.m. in this auditorium. Today's seminar, today's talk, is entitled A Computer Scientist Looks at the Energy Problem. Right away, you know that looking at the speakers that this is not the proper title for this talk. It should be Two Computer Scientists Look at the Energy Problem. We are very, very pleased and honored to have both Professor Randy Katz and Professor Dave Culler from the Electrical Engineering and Computer Sciences Department here at Berkeley as speakers today. Randy received his undergraduate degree from Cornell University and his master's and PhD here from the University of California at Berkeley, joining the Berkeley faculty in 1983, and since 1996 he has been the United Microelectronics Corporation Distinguished Professor in EECS. David Culler received his BA from Berkeley in 1980 and an MS and PhD from MIT in 85 and 89 respectively. Joining the faculty here in EECS in 1989, he is the founding director of Intel Research at Berkeley, and he is a member of the National Academy of Engineering, an ACM fellow, and was selected in Scientific American Top 50 Researchers and Technology Review 10 Technologies That Will Change the World just recently. So let us welcome these two distinguished speakers with our usual warm welcome from CITRIS and look forward to this talk on computer scientists looking at the energy problem. We're going to start with Professor Katz. Randy.
Thank you, Gary. Never start a talk with an apology, but as you can tell from my voice, I'm not operating at 100% capacity at the moment. I did take some kick-ass decongestant just before the talk, so maybe my head will blow off, and that would be very entertaining during the next hour. As Gary said, yes, this should be, I guess, two computer scientists look at the energy problem, but since David and I are joined at the hip, maybe we're just Siamese twins. So what I want to do in this talk is present the bigger picture of how we perceive the energy problem to be, and to talk about information technology, my part of that footprint, computer and communications equipment, how it consumes energy and how it could do a better job of being more efficient in that consumption. Then I'll switch the floor over to David to talk about how greater information awareness of how energy is used can be exploited to improve the overall efficiency of the generation, distribution, and usage of energy everywhere in the energy system. And we have some summary and conclusions at the end. So one of our favorite charts, which I think we originally got from Arun Majumdar, our colleague in mechanical engineering and formerly division director at Lawrence Berkeley National Lab, is the so-called spaghetti chart that shows all the different sources of energy denominated in quadrillions or quadrillions of BTUs or some unit of energy. And so you see on this side of the chart, hydropower, biomass, all the way through to natural gas and petroleum, the various places that energy comes from. It is interesting to see the relatively small intrusion thus far of things like wind and solar power as sources of energy. This is, I believe, for the United States. As the energy is extracted from these various sources through a variety of different generation technologies and then distributed through the various systems we have for transmitting energy at a distance to where it is used, a lot of it goes up, if you would, in smoke. So there is inherent inefficiencies in taking a barrel of oil and turning that into electricity. And then there's somewhat less inefficiency, but still some inefficiency in moving that electricity from where it is generated, let's say in Nevada or Arizona, since we don't like those kinds of plants in California, to where it's used here in the San Francisco Bay Area. So there are lots of losses that take place in particularly the electrical generation and distribution piece of this energy pie. And we are particularly interested from an electricity as a source of energy in its use in residences, commercial spaces, and industrial uses. And you see how that is blocked off on this side of the chart. And so it kind of more or less breaks down to residential plus commercial equals industrial. It's about one-third of that compared to vehicular uses that tend to make use of things like petroleum. But of course, increasingly, vehicles will also make use of electricity. So we're particularly interested as IT guys, as worrying about the energy use and consumption from the electrical piece, both in terms of its generation, its transmission and distribution, and its usage, with an understanding that it's going to only get bigger over time, or demands for electricity are only going to get bigger over time. Now, last year, when people were worried about high $3 a gallon gasoline, there were things like this that appeared in the press. The right thing to do is to get off of oil and move towards electricity, and think much harder about smart grids and more efficient generation, distribution, and usage of electric energy in electrical form, rather than use petroleum that we have to bring in from countries that we don't like, in parts of the world we don't really want to have anything to do with. So this, of course, has sort of disappeared again, but this morning as I was coming up to campus, I saw gasoline is back in the low $3.25 a gallon, and so hopefully this debate will continue about alternative ways of getting us off of the petroleum as an energy source. There's a lot of things that are happening in the computer world which are making us think about computing as more industrial and more as a utility, particularly the migration of computation from desktops into the internet infrastructure, in particular in the form of cloud computing, a term you may have heard about. And people think about that as kind of turning computing into a utility. You plug into it, you use it, you pay for what you use. A lot more applications are being hosted inside the network rather than on the edge devices. We all spend time doing internet searches using Google. We don't have to have the entire search engine on our own end devices. Things are moving, migrating in terms of where computation actually is done into more centralized, more industrial scale facilities, which is what's happening on the computing side. And of course, computing also is going into the physical world in terms of sensors that can communicate, can actuate and control. And so you can imagine putting more controllability into the physical world. So IT is consuming more and centralizing more on the one hand, but also providing a framework for more distributed and decentralized awareness and control as it moves out into the physical world. And these both have issues or opportunities associated with the way this will affect our energy infrastructure in the United States and in the world. Now, Jeremy Rifkin is one of these futurologists, future thinkers, and he said something I think very interesting. In his view, I think historically the first industrial revolution is pretty much the introduction of machines, so we can amplify our physical power by having steam-age machines do work for us more than any single person could do. The second industrial revolution was the information revolution, the way in which we can extend our cognitive capabilities, our ability to process and manage information. And he sees this third industrial revolution as being the combination of these two, of how do you exploit better awareness, better use of energy with information to bring mankind and society to the next level. And so he's a big proponent of this decentralized, distributed model of how to generate, distribute, and use energy compared to the centralized schemes that we find in the world today. So that's a little bit of the big picture. Let's talk about information technology as an energy consumer. And to put it in a little bit of context, this is from a very interesting report that came from the Climate Group that extrapolates energy demands to the time frame of 2020. It's only, order 10 years away. It's a very nice study that if you have not seen, you could Google it and find it. It's very worthwhile reading. And one sector of particular that they analyze in this report is the information technology's contribution to the carbon footprint, if you would, as it will be extrapolated 10 years into the future. You see the amount of carbon dioxide equivalent for PCs, peripherals, and printers, which is about 60% of the footprint. Telecoms and devices, our little handhelds, are 25%. And surprisingly, this notion of data centers comes up on this as order 18, 20% of the overall pie. So they're extrapolating this centralization of computing into this industrialization in the form of internet-scale data centers as being a very significant place of where computing will take place in the time frame of the next decade. This total pie in 2007, IT as defined by PCs, peripherals, printers, telecom, and if you would, data centers, which could be the basement of Quarry Hall or the basement of Soda Hall, as well as the computers at Google, represents about 2% of the world's carbon footprint. While that doesn't sound like a really big number, all computers rolled together is only 2% of the carbon footprint of that kind of activity. It's comparable to the global aviation industry. So it's significant, even though 2% may not sound like a big number. But even of greater interest is the fact that it is likely to double, or is extrapolated to double, predicted to double between now and 2020. So it's a part that we should really be concerned about to try and understand how we can manage that. And of great interest to me, because of research that is ongoing here at Berkeley in our RAD lab, and because it's an exciting part of really the information technology research arena right now, is in the area of internet data centers. And that turns out to be a fairly significant chunk and a rapidly growing chunk of this. Now again, this climate group's extrapolations, here's the global information communications and telecommunications energy footprint by geography. And the bottom line of this, I thought I had an arrow there. The bottom line of this from 2002 to 2020 is the dramatic growth in the parts of the world that are outside of North America, primarily the rapidly developing geographies of China. Part of the reason why IT footprint is so large in China is a combination of the fact that they're using a lot more computing equipment, expected to use more in the next decade, but also the sources of energy that they use are not particularly environmentally friendly. So this factored into these analyses are, what is the source by which electrical energy is generated? Is it coal-fired plants, or is it some alternative like hydropower in figuring out the footprint? And this is why China becomes such a big picture, a combination of its rapid growth, but also the unfortunate story of the way in which electricity is generated in that part of the world. If we look at by subsector, in other words, telecoms, data centers, and PCs and various computers, again, between 2002 and 2020, the most rapid compounded growth is in data centers, again, representing the centralization of the computing infrastructure. Very influential observation was made by researchers at Google, Luis Barroso and Urs Herzl, of how inefficient our current computing infrastructure is. They made the following observation, that our systems are not particularly energy proportional. It is highly desirable that if you use them less, they should use less energy. Of course they do, but it does not scale in the same proportion with the usage. In other words, a computer that we're using at 100% of its utilization and 100% of its rated power, if I were to use that computer at only 10% of its capability, I will probably continue to use 60% of its power. So we don't have that linear reduction in the power consumed and the energy consumed as we scale down in our usage of machines. Now, the reason that this is important is that even Google, which is the world's probably most efficient user of compute cycles, they have a lot of work they can assign to their computers. Their observation from this chart is, on average, the vast majority of their machines are kept busy 30 to 40% of the time. It is extremely difficult to load computers to 100%. just because of the vagaries of how long it takes things to be done, how aware you are of where slack resources, how to harness it by giving it something useful to do. People have been working on the computer scheduling problem for 50 years. Google is really darn good at it. They can achieve, at best, 30 to 40% utilization. And those machines are highly inefficient when they're not being used at 100%. So right there tells us that there are some principles that could be exploited if we could only do a better job at harnessing the fact that we're not using those machines, either give them some work to do or figure out how to save more energy when they're not working at their full rated utility. So they introduced this notion of energy efficiency, which is the utilization over power. What you would like to have is the red line, which trends towards 0 as you use your machines at sort of order small percentages of use. What I've shown on this is the typical operating region of 15% to 50%. And you see that we are far from really finding ourselves in that efficient energy range. Now, my colleague David Culler came up with this fantastic catchphrase for our project, which is, what we need to do is to be able to do nothing well. Because most of the time, our computers are doing nothing, but we're not very good at doing that nothing well. And so really, this is a huge challenge for the information technology community to be able to identify those periods of low utilization and put our systems into these low power states. It's not just a hardware problem. There are low power states in modern microprocessors. It's the operating system. It's the network services. It's the keep alive messages over the network that all together make it virtually impossible to put that machine to sleep even when it's sitting on your desk doing nothing. Even in the highly managed environment of Google, their machines are not used more than 30 to 40% of the time on average. And they're very bad at being able to exploit power savings in those cases. So we need to figure out, with a holistic approach of understanding the context of computation, what is going on in order to be able to really exploit scavenging and finding those opportunities for power savings in our information technology systems. Now, one of the things that is interesting about the analysis that the Climate 2020 group did was, I know these are a little hard to see, but this is supposed to be the energy footprint extrapolated from 2002 all the way up to 2020 for data centers. And one of the big things that they do in their sort of analysis is this magic, and we will reduce energy through technological innovation chunk, which is the arrow that's pointing in that direction, I guess in this direction. So this part of their extrapolation is, if we do nothing, if it's business as usual, we're over here. But due to technological innovation, friends at CITRIS come up with some good ideas. We hope to be able to be operating at this level. So they sort of, in their analysis, they've worked in, and now a miracle happens. Well, hopefully it's not really a miracle, but it's some real technology that can be developed. So let's talk a little bit more about internet data centers. They're purpose-built buildings designed to have heavy concentrations of computers, and lots of computation per square foot. They integrate a lot of facility systems within these buildings, not just computers, but power distribution, large-scale air conditioning, and so on, in order to deal with the heat loads that come from highly packed equipment, and lots of computing and storage and all the different things that we expect to find in computer rooms. They often have a rather complex, albeit local distribution system that provides redundant power, converts the power at various levels in order to deliver the necessary power to where it's needed to the racks of computers. A common factor that's used in describing these things is power utilization efficiency, or PUE, which is intended to capture, if I were to just power the computer equipment, I would have a certain amount of power consumption in my building. How much extra overhead is associated with the distribution system itself and the necessity of cooling both the distribution system and the computers? So PUE is typically in the range, for most modern data centers, in the range of 2 to 3. What that means is that all the infrastructure in support of the computers uses 2 to 3 times as much power as the IT equipment itself. So there's a pretty heavy overhead associated with feeding and cooling the equipment, not just the equipment itself. And this is a pie chart that shows some of the sources of where that energy footprint goes. The chillers to cool the machine rooms, the air movers, the so-called cracks, computer room air conditioners. The IT equipment in this particular one is less than one-third of the overall energy pie that goes into a typical data center. PDU is power distribution unit. UPS is uninterruptible power supply. So many places in the data center consume energy. We have to worry about a lot of the mechanical engineering design of these things in terms of moving the air around, and there's a lot of knowledge of how to design these kinds of systems for a certain level of efficiency, but one of the things that strikes me as a computer scientist is the goal here is to pack the equipment as closely together as possible. That's, after all, why we build special built buildings, is to pack them full of computers. But you can't put them together as tightly as you would like because of the heat load that is generated by those computers. So you have to space them apart. Maybe there's a way of thinking about more distributed architectures that don't seek to achieve the highest density in the small places inside the data center. In other words, a system perspective of how to get the most computing over a large area rather than build a box with the highest possible heat density and not be able to pack them as densely as you would like because of the aggregated heat load. So a lot of innovation that people have been investigating in terms of air movement in these environments. Alternative ways have come up of how to organize the packaging of these things. One very interesting approach is to use containers. There are spaces that don't require humans to enter them, at least not very often. And so you can do things like move air at velocities which are typically impossible to do in typical machine rooms. So very fast-moving air in order to evacuate the heat. You can set up the topologies of these spaces to be very also efficient in terms of how the air moves over the equipment that's inside of them. This is really quite taking off, and another view of a sort of view from inside a container. There's a lot of packing advantages to thinking about this as the unit of replication rather than an individual processor node or even a rack. If you need more computing, just roll in another container, stack it on top of the containers you already have. It's a self-contained cooling power distribution system with computing, networking, and storage embedded inside the container. They don't really show where the pipes come in and go out or where the giant electrical cable comes in this picture, but I think you get the idea. If you want to see what one really looks like, this is a capture from a video of Google, who about 6 months ago announced that they have actually deployed a containerized data center as part of their processor complex, their data center complex. So each of these little things up here that are kind of a little hard to see, each one of those is a container. You can go on YouTube. You can take a tour of one of them. You can see the repairman go into it. And unfortunately, the guy has a bit of a comb over. And so when he walks into that space, it's a little embarrassing, but nevertheless. And it's not just Google that's doing this. Microsoft in their Chicago data center is using a similar design. Again, it's a little hard from these, if you would, People magazine screenshots that I have here. The paparazzi view of what's inside a Microsoft data center, it does kind of give us a view of these things up here are installed containers. And so this alternative way of thinking about packaging of the machines is really coming to the fore. Now, one of the things that has happened recently is Google has announced what their efficiency metrics have been able to achieve by a combination of lots of facilities magic. And they are able to run their data centers today at a PUE not of 2 or 3, but at 1 1/4. So by being careful about airside economization and more efficiency in the way in which you build the chiller systems and a whole host of those mechanical engineering things, they have managed to reduce the factor of 2 or 3 down to an overhead of only about 1/4. What that means is the real challenge for us as IT people is to figure out how to get the power consumption of the IT equipment down. It's no longer about worrying about the air conditioners and the air movers. It's about worrying about how to do nothing well in the IT equipment to get the one part of the 1.28 to be a smaller number. And this is just some more data from Google showing some of the variation in their PUEs as a function of time and data center. Now, imagine you were going to build a million server data center. What might it look like? And I wrote an article for IEEE Spectrum at the beginning of the year. I think it came out in the February issue, and we sort of extrapolated forward to what a 1,000,000 server data center would look like, and it kind of looks like a gigantic warehouse space where the containers are driven in and parked. And this is before we got to see those sort of video clips of the Microsoft and Google containerized data center, so it's not too far off from what those things look like. Note that they're not stacked one on top of the other, and there is some extra space in there because you do have to drive the trucks in to install the containers. So again, a systems view of total capacity and so on, you have to really think about the access space and things like that. So here's how the numbers kind of work out. 24,000 square meters, housing 400 containers, each with 2,500 servers would get you 1,000,000 servers. We figured out, sort of by back of the envelope calculation, that unless you did something special, we're talking about 300 megawatts, which is a big power station. That's really big. I don't know, I think a typical house is order 1,000 kilowatts per day, 1,000 kilowatts of power integrated over the course of a day, so multiply it by 24 hours. This is really the equivalent of probably a metro area, a large number of users. And so, again, you need all sorts of complex facilities associated with this, because when you have that many computers in one place, any failure in the cooling system, any failure in the power distribution system would take out too many computers. It would be too disastrous to the service provider. So you have to think of all those redundancies and additional complexities associated with that. So with that, I'd like to turn the floor over to David to talk about now IT as a way of how do we exploit IT to reduce the power demands of the systems that are of interest to us, and also in buildings.
300 megawatts. So I guess we'll go a little bit speedy here.
Is your mic on, Dave?
Is that better? I could use yours. Poster have disappeared, so that must be good. You already have a sense of how interdisciplinary this problem is, and I think that's one of the goals of our talks today. Yeah, 300 megawatts. Typical household burns, on average, a kilowatt, so 300,000 households times 3 people, just about 1,000,000 people. So I guess that's about it. We're, from an energy point of view, roughly equal to a processor. What I'm going to try to do with this other part, what you saw in that was really looking at buildings, buildings that provide a certain set of operational services from a completely different point of view. And let's begin to broaden that and look at the larger piece of that spaghetti chart. And you know, we inherit today this marvel of the industrial age called the grid, from the generation, transmission, into distribution and eventually consumption, which we take for granted. In fact, for 100 years, we've been encouraged to take it for granted, that in some sense, the Industrial Revolution, the growth of the nation and its economy has really been built on that assumption of oblivious consumption of cheap, high-quality power. And if you just think of it from the point of view of this commodity, it really is a marvel that you are asked today to build the national grid, or the 5 national grids. So what I want you to do is deliver extremely high-quality power at low cost, and substitute any other commodity into this, to millions of customers over thousands of miles, synchronized to 60 hertz, so fractions of a millisecond variation, with, of course, nobody ever places an order. You have no forecasting. You have no plans. And there's no inventory anywhere in the supply chain. Right? There's no other commodity that you... And in fact, it's hard to believe that if we were posed with this problem today, rather than having grown into it over 100 years, that we would even believe that there was any way we could possibly solve it. Obviously, we've got an existence proof. And in some sense, we've done that because it was so fundamental to driving the ability to industrialize by essentially being oblivious to our energy consumption. The picture, of course, is a little different as we look at these other potential sources that we'd like to utilize. Nice picture there. Actually, did we? Randy and I shared this back and forth, and Okay. Guess I didn't track that. Sorry about that. Get back here in a second. So, obviously, this picture we've had, and we often refer to the supplies as dispatchable, meaning given some prediction of what these loads are, because of course you can plug in any load anywhere and it's supposed to deliver electricity to you. We have this very, very sophisticated system of predicting and estimating the loads ahead and then adapting them as that load is actually delivered through a generation, transmission, distribution system. So the big changes afoot, well, in large part, is that those renewable sources, to a very large degree, are not dispatchable. We will make solar energy, we will convert solar energy when the sun shines and wind when the wind blows. So we no longer have the control of building on my tiers of nuclear and coal-driven and fuel-driven and peaker plants to try to feather the load to the demand. So what are we going to have to do if this is going to make sense going forward? And the answer is pretty clear, that we've got to populate that lower right corner, that we have to now create loads that are in some sense are dispatchable instead, that our loads now have to be able to adapt to the availability of resources. And since we're going back 3 millennia, since we're already have recently crossed a millennium, it's make hay when the sun shines, right? That you want to utilize energy when it's available and begin, rather than be oblivious to it, become aware of it. And what that really means is begin to communicate. So why is it that no building bothers, even though it's very predictable? It doesn't bother to forecast its load or consumption going forward, or other than these very infrequent and extreme cases like we're about to have a blackout right now, would you please feather a piece of your load, that the supply side, the utilities need to be communicating back. So you could imagine a future grid that was fundamentally cooperative in its two elements. How do supplies and loads cooperate together to deliver that high quality service, hopefully less of it, and hopefully in a manner that consumes a lot less. So that's what this Project Low-Cal that Randy and I are newly started. Obviously low-cal in the sense of lower calorie, using less, but also really utilizing local generation and storage as a basis, utilizing the unique local properties that are so ubiquitous in the energy space, so many different forms of energy, different consumption, and of course it's here at Cal. So in some sense, it's how do we go from a world of primarily dispatchable supply to a world that uses overall less, and a lot more of what it uses is that non-dispatchable, renewable, less costly from an environmental point of view. What are the tools we have? Really, we have 3. And Randy mentioned a really important one. We often get into all these exciting things about the way we feather the active part of our load, where the vast majority is just plain waste. And the problem is, it's not like you can go look up the waste in the W's. It's that the waste is so pervasive. We find so many ways to squander energy and electricity, partly because of our 100-year history of being just oblivious to it, but also because there's so many little details that are the reason that we're cooling and heating buildings with nobody in them. We're spinning computers, as you saw, that utilize huge amounts of energy when they're computing nothing. Once you solve some of that, the load that you're presenting to the grid is actually much more difficult to solve, to supply. Rather than everybody out there, and I'll show you some data, just consuming energy constantly, they become highly variable. They become highly variable over time. So how do we schedule that more highly variable load? And how do we begin to decouple the supply side and the consumption side so that we can schedule it and use energy when it is available? So we're going to explore in the rest of this some of those techniques. Bottom line here is that it's no longer the case that we have to think of the only copper in the world pushes electrons, that every place where we exchange electrons, we should be exchanging information. And the goal there is to make it to where the loads not only are aware, but then they become sculptable, that we can begin, and we sometimes use the terms of peak shaving or load shifting, which is getting at kind of the margins of adjusting consumption so that it matches perfectly what the supply that is available. And that means forecasting demand. That means adjusting load according to availability. It means the two sides actually negotiating with one another. And that may even have some teeth in it, that you forecast that you're going to consume a certain amount of load. If it's provided to you, then you use only that much. So those are, in effect, you'd like those notions of adaptation and demand response to be intrinsic in the system. So if that's the thrust of the research investigation, it's kind of a big picture. How do you boil it down to things you can make headway? How do you start? Where do you start? And the answer actually is pretty simple. If you're focusing on electricity, you already got the picture of it. Randy says computers. That's a really good place. But more generally, it's buildings. So why buildings? Well, because they consume three-quarters of the electricity supply. They're also about 40% of the total consumption and a little more than that of greenhouse. Yeah, the utility bill is not bad, $370 billion nationally. Yeah, okay, construction and maintenance is about 10% of GDP. But moreover, not only is it three-quarters of the electricity, but it's where all the coal goes. It's also where the best opportunities are for utilizing renewables, because they don't move very fast, these buildings. They're fairly predictable, right? That we have all of these tools. We can talk about energy storage that doesn't have to be light and high density. It can be stationary. It can be down in the basement or under the basement. So we have a whole set of opportunities as we focus there in particular. We also are very familiar with them. So one of the pieces of efforts ongoing, partly through this project and others, is begin to use campus as a living laboratory. And we can ask the question, how do our buildings look? So this picture shows, in the vertical axis, the total kilowatt hours per year consumed by various buildings on campus. We sit here on campus and we consume about 200 million kilowatt hours per year. So you would expect the total consumption roughly to increase with the size of the building. What I've got in the other dimension isn't the size, it's the energy intensity, density, the kilowatt hours per square foot. So average nationally for commercial space is about 15 kilowatt hours per square foot per year, or if you will, about $2 of energy per square foot. And on average, campus is about average. It's not like Lake Wobegon. We're about average. But also notice that our newest buildings are not highly green and energy efficient. They're going up and to the right. So you would expect that if it were just the consumption versus the size of the building, all of these dots ought to line up vertically. And what we see is that small buildings are really low density, appear to be relatively efficient. Soda Hall is a 500 kilowatt light bulb on day in and day out. I'll show you a little bit more of that. In fact, I guess I could show you that picture today. It almost never gets below 400, even when we shut it down over Christmas. It's amazing how poorly we do nothing in that building. And if you think that's surprising, Corey Hall is a megawatt light bulb and has only 5% variation from peak to mean. And so, of course, the big question, Paul Wright just left, but where do we expect CITRIS to be? Well, actually, CITRIS is about Corey plus soda combined. It'll probably weigh in at about 1.5 megawatts. And it's also in square footage, about the two of them. So campus as a living laboratory is actually very interesting because it's got buildings dating back from 100 years to not quite finished yet. That Soda Hall is a great example, essentially, of Silicon Valley IT loads. Corey, and soon with the Nano Lab here, is going to be all of your semiconductor load. Stanley, oh boy, those guys are doing great. Look at that. They're up there at 4.5 times national average per square foot. Doing what? Well, they're typical of biotech loads. And so they do nothing even more poorly. And what is that? That's all the refrigerators with nothing in them. That's the hoods that are moving air that's not contaminated. A lot of it is in there for good reasons, which is also policy gets interwoven with the family of these. So a step is to just understand how is it that we do nothing so poorly to go after the waste. And this is just giving you an initial breakdown of soda hull. You can see the chunk at the bottom. We waste about 200 kilowatts day in and day out to run about 500 servers that are mostly doing nothing in soda. And then there's a whole big chunk of it that is your desktops. And then there's a modest portion is the remaining of the environmental load. So that's one. When we talk about buildings, you really want to think about there's a certain amount that's an environmental load, and then there's an operational load. And the kinds of things that we do to do nothing better, and those two are relatively different. Randy talked to you about many of the things that we're doing on the server side inside the data room. Actually, I want to do a little quick promotion here because many of you might say, well, what can I do on my desktop? And there's also a lot that's going on there. And let me, oh, if only I was connected. So if you were to go to there, you would see some of the programs that we're putting in place with some very nice tools that allow your desktops to at least go to sleep very well in the large variety. We have a green soda project, and we have a green Cori project, and our folks in mechanical have now put 150 nodes of their instructional computing. We're using this lovely tool called Auto Shutdown Manager, which I would illustrate, but maybe when I come back. So there's lots more that we can all do just in the routine, our everyday lives. See Gary checking his watch, so let me get going. Okay, so another question of how do you get going with a project like this? Where do you start? We want to begin rethinking the electric grid now that the internet already exists. Two paragons of national scale design with completely different principles, right? The electric grid, highly centralized, synchronized across the entire extent, controlled for a central authority. The internet, highly decentralized. We use intelligence at the edges. We don't have smart cores. We have a stupid core. Maybe the best smart grid is one that's stupid in the middle and smart at the edges, and uses that intelligence then to obtain reliability over and beyond what the whole can be. So a question here is, where do we begin? And if you start with the notion, well, let's begin by designing a new electric grid that utilizes the existing internet, the answer is probably not in our lifetime. So we actually have some experience. So it's a fact. The grid exists. We ought to exploit that and use that everywhere we want. And, of course, the internet also exists. And there's a parallel here, too, in the design, in that when the internet began, it was an overlay on the phone network. We didn't build the internet first. We wrote some code and attached some drivers and then carried data traffic over the phone lines. And so, in effect, we utilized an infrastructure that was very much like the grid, highly centralized, controlled by monopolies, huge sunk investment. And then as the internet became more and more important, eventually it sunk down into the core, and now the vast majority of data traffic is carried on top. So that's actually a reasonable picture about how research in this area is likely to play out. And what Locale looks at is that should be a goal rather than just an artifact of how we conduct our research. That what we really want to do is to create a new energy network that is an overlay on those existing infrastructures. And then over time, as we understand those solutions better and can optimize for them, you can imagine that intelligent energy network sinking down into that pair of national scale infrastructures. And in the meantime, we can talk about particular pieces of that being bound to those underlying physical resources, which means we can also think about having virtual grids and our own localized grids, much like we have virtual private networks and we have overlay networks for doing sharing of things that may be legal or maybe not legal. We can think about in the energy space that there really is notions of energy subnets that have well-defined sets of producers and consumers that can cooperate together to balance the production, the consumption, and the transmission from the two sides. And that's really what Locale is driving at, is putting in place the set of observations you need, measurements, protocols that the two sides could go together. So if you will, you could think about a world where rather than an oblivious grid, you have a cooperative grid, and rather than oblivious consumption, you have aware. So I've drawn the picture here with the cloud, because that's how we like to view the internet, being superimposed on the existing grid, which means every one of our buildings, our data centers, are aware themselves of their consumption, their patterns of use. They're able to forecast. They're able to make a reasonable statement about what they need. And they're then able to monitor, model, and begin to mitigate that. And the kind of pieces that we're focused on there, what are the means of instrumentation so you actually know where your energy is going? What then are the actions you take to eliminate? It's nicest to eliminate the waste first because that's all free, right? We're doing nothing. Let's just do nothing better. Then we can focus on the active parts, actually doing them well, through mechanisms of shifting, scheduling, adaptation. But the other pieces are now, as a norm, enabling communication from the demand to the supplies and in the other two directions. And that means forecasting. That means tracking to the forecast. It means engaging in various large or small markets. It means articulating availability so that you have something to plan against. It means pricing and other mechanisms so that you can get the two sides to conform from one to another. So that's the big picture then of where we're going. Let me give you an example of what we imagine might happen in a building not too far away. So if we imagine, for example, in Soda Hall, that if we're done and Randy has accomplished all of what he just talked about, our data center would in fact be power proportional, and it would be its own energy network. Let's call it the machine room energy network, with various kinds of devices in it using its energy very effectively, and in particular harnessing all of the idleness in there. That's now one more load, if you will, within the family of loads in the building, but one that you could sculpt, one that you could adapt to availability. We can also ask the question, what is the building-wide energy network? How are the family of chillers and air handling units and other things that are providing the environment, how are they interacting with one another to schedule those overall loads, and how do they trade that against the set of loads, say, in the machine room? How does the machine room representative, what we're calling an intelligent power switch, represent the family of things that are going on in there? And similarly, how would now some intelligent power switch represent that aggregate of loads in the building to, for example, the various supplies? And one of the beauties of a virtual energy network is those supplies could be not necessarily here on campus, but out there at Altamont Pass or at Richmond Field Station or in Texas, to the extent now where the two sides can work together. And you could imagine maybe the building is articulating a forward-going load profile of what it's going to use over time. And maybe these supplies are saying, well, if you do that, I'd charge you like this. And then maybe over time we're tracking that those two meet. Okay? But those would be the kinds of operations we would expect to be happening naturally without our attention to it in a localized grid. Okay. So kinds of research questions we're digging into then. I've mentioned some of them about understanding where it goes. In effect, what I'm introducing is a notion that loads have slack and I can move that around and schedule them. How much of them? What are the fundamental limits to renewable energy penetration? By introducing scheduling and storage, can I go from 3 or 4% to 30 to 40 to 70% of non-dispatchable resources? And what are the kinds of protocols involved, the system and network architectures, and so forth? So one piece of it I've touched on is hardware-software device that glues together these kinds of things and provides the facilities for communication, aggregation, and so forth. It's shown at least diagrammatically here that scales up and scales down. Another piece are systematic ways of breaking down all of the loads that present themselves in a complex ecosystem like a building in order to know where it goes. And you can ask then, what is the monitoring architecture? What would be the equivalent of the layering we see in networking, the physical layer of instrumentation, the networking layer of moving that around, the higher layers of making sense out of it? In order to this, you can imagine when this took place. So this is a fine-grained breakdown of all of the energy used in the RAD lab, for example, on a very important day back in January. But more importantly, how do we take that low-level information and re-aggregate it back up to where we're spending that information to what purpose? We can ask the question, what would be the operating system for the data center that manages all of those resources and allows us to put higher-level applications on it? Or the operating system for the building? Or, if you will, the operating system for the bid? How do these distributed bodies of intelligence actually work together to get these devices to operate efficiently and cooperatively so that we can begin to scale it up? It's not just primitive market mechanisms, but those with various other higher level mechanisms, forgetting, for example, virtual communities within a grid to work together so that the consumption in Randy's data center perfectly matches the wind that's blowing in Altamont Pass plus a bit of solar that's scattered around through Berkeley. So those are the kinds of questions we're looking at. How do we move from designing to peak and consuming it obliviously to designing, capacity planning to average, and then putting in place the monitoring, mitigating, modeling to operate at that point? Last two, did you want to do these, Randy?
I think maybe we should stop here and just take questions.
Okay. I think that's good in that, let's shift that around. Thanks.
Thank you both very much. One of the things that I love about this project is not only are two of the smartest people I know working on it along with their colleagues, but they've been kidding us all along. They have told us they've been working on the internet for all these years, and now they're so out of the box into this very, very important space, bringing new thinking to a very, very big problem for the planet, and that's wonderful. I really admire what you're doing. Let us take questions. Lori has another microphone back there. We have one down here, so let's start.
Hi, I think it's really interesting to compare internet against the energy network. And I've been hearing that one of the fundamental difference between information is energy is that the transmission loss. So for energy network, it has to be granularized. It has to be optimized in subnet level. So what do you think about how this would affect the architecture of the energy network?
So in both cases, transmission distribution has to be optimized. And one interesting case is that in the information networks, we have the ability to buffer information in order to obtain higher reliability or to obtain higher performance by moving it when it's convenient and when it's inconvenient. And so one view you could say is, isn't it amazing? Where are the buffers in the grid? Why are there no buffers in the grid? This is crazy. How could we ever decouple it? How could we get higher reliability? Well, and you say, well, because it's technologically so hard, we just don't have good storage, which is true. We don't have good storage. The other view you could say was, well, wait a second. Electrons are much easier than bits. You know, when I send information around, I have to get the right information from the particular source to the particular destination. Energy's simple. As long as it goes, enough goes in and goes out, who cares which one's got which electrons? Couldn't care less. So arguably, it's an easier networking problem. Now, there is this little gotcha that we don't have very good storage today, but how much of that is because we haven't looked deeply enough at the problem? Well, actually, there is lots of bulk storage with pumping water back uphill to reservoirs and underground caverns. What we don't have is kind of medium-scale storage. And we have a tendency to think that batteries have to be light and in flashlights in cars and very high density. Well, you know, maybe the basements of all of these buildings should be full of some storage capacity. In places like Merced, we have a huge tank of water for exactly that purpose. So it's not clear that we've really thought about it from a systems point of view that would also give us, between scheduling and storage, the ability to decouple and optimize.
I'd like you to comment on the smart grid standards work that's going on nationally with NIST, and if you have any concerns and optimism or advice about that topic.
So do you want to...
Why don't we alternate?
Yeah.
So I think one of the things that is also a very interesting analogy in this area of energy systems with things like telecommunication systems, that there are entrenched players, there's a regulatory environment. You can't avoid the policy dimension to all of this. But one of the things that people in the telecom world have learned is that often that regulatory environment will squelch interesting alternative technologies because, you know, it just doesn't make sense to do something at a particular scale or to stick something in an architecture because of the way things have been standardized. So I am somewhat concerned about how relevant some of the things we are looking at could be, because while we're looking at a more decentralized kind of solution, the natural pressures of the standardization efforts are towards who in the system has the control of the information. It tends to centralize it because of entrenched players, namely the utility companies. So we want to look at the best kind of solution for this kind of thing. There are opportunities for its deployment and use in independent environments. For example, university campus appears as a single load, if you would, to PG&E. There's lots of locale things that could be done at the level of these kinds of structures that allow you to really, you know, believe that you could deploy this kind of thing broadly at that level. It would be nice to think about how to be able to deploy it even more broadly than that.
Let's just take one more question right here.
My question is largely answered by the answer you just gave, but just a couple of additional points. When you analogize to the creation of the Internet as an application on top of the phone network, nobody had to negotiate with the phone company or the government to, you know, have two people with modems and inventing some software, and they could come up with the Internet independently. So again, it's back to the issue of what policy impediments you have to overcome in implementing this idea, and you alluded to it or sketched it right there. So I'm assuming that you largely start with the consumer side and you build some kind of load balancing system for a building, and you can do this independent of the policy issues.
So let me pick up on that and extend it a little bit. Similar today, I don't need anybody's permission to get a collection of loads to perfectly match a collection of sources. The ISOs of the world, or, you know, there's lots of good information about what the supplies are and the bottlenecks throughout the transmission. I can demonstrate that, in fact, these loads match those and would not have overbuilt. So the standards and regulatory policy do not have to be the limit to innovation. And I think from a research point of view, that's a key thing. And maybe we can even introduce a culture of standardization by rough consensus and running code, which comes from the Internet side as opposed to agreement. Now, in many cases, there's huge long lists of standards that have nothing to do but framing the bits. You know, every 7 years we get another industrial information standard driven by some new business, and they actually have no content. And, you know, if they were XML, you'd say that's half a dozen schemas. Big deal. Why did we spend 35 years? So there's a lot of it that really shouldn't be holding us back. Now, on the other hand, when it rolls out into production, you need to have all of those things in place. And that's actually a goal, that you should be able to innovate and prove and then roll it into production and nail the rest of the standardization. And I think the previous question was getting at Steve Chu has recently articulated, here's the 10 standards that matter, and gone back, for example, to the IETF and say, well, you tell me what are the core RFCs that I... That's a great process to introduce into that. It's not inconsistent with innovating by using the information resources we have, the electrical resources we have, putting protocols that show, you know what? Here actually would be a viable working virtual grid where supplies and loads cooperate with one another. And they happen to be doing that through this underlying machinery, which over time now could begin to trust that that cooperation is a good means of reducing cost and increasing reliability. So I see it more as building up trust over time. And I think that taking this overlay approach, we have an avenue of getting there.
That's all the time we have. Thank you both very much for a very inspirational and informative talk. Thank you all for coming.